All right. Hello. Hope you guys had a nice weekend. So today we're going to talk about the Google file system. I'll try to provide a little bit of context for this. Unfortunately, it probably would have been helpful. How many people are familiar with the design of NFS? Any sort of networked file? How many people have ever studied any sort of distributed file system? Okay. This is in Steve's class, or? Oh, okay. So it would have been fun to read the NFS paper before this paper, but this paper is more up to date. So, but some of what's interesting about this, I'll try to explain as we go along, because there are some assumptions that previous file systems made that Google file system is relaxed, right? And we'll talk about why they did that. Announcements: the exam is a week from today. I think is it in this room? I think it is. So. Exam procedures, I think it's in the evening. Anyone remember? I guess I should know this. Let's see here. Remind myself. So I think it's a week from today, like 4 to 7 or something.
Like 3:30 to 6.
Yeah.
3:30 to 6.
Okay. So the format will be the same as previous year's exams. So go on the website. There's two examples now of previous final exams for you guys to look at. We'll use the same format this year. You have a question, Mac?
Are you still going to be releasing like exam questions?
I don't know. How many have you guys got a feedback form to fill out about the class?
Yeah,
Okay, cool. So I will start. Yes, the same deal will apply. I'll post it on Piazza later today. They don't always tell us about these blessed events. So, and I need to make sure I can monitor your progress. But again, it'll be the same deal. Unfortunately, there is no exam yet. So if you guys have already passed one of the thresholds, which I very much doubt, I don't have any questions to release. But once you guys start, hopefully by the end of the week, we'll have an exam, and you guys will be over the magic number required to get access to some of the questions. So if I remember correctly, there are 3 long answer questions of which you need to answer 2. There are 2 medium answer questions. The long answer questions are going to be more in-depth and more conceptual than the ones that you guys answered on the midterm. The midterm questions sort of map to the medium answer questions that will be on the final. The short answer questions on the midterm will be quite similar to the short answer questions on the final, and there will still be multiple choice questions. So that will be the format. And again, if you guys want to see the exams of previous years, which I think will give you guys some good practice, those are up on the website. So check them out. What else was I going to say about the exam? Nothing. And then the assignment 3 is due a week from Thursday, if I remember correctly, at midnight. So next week we will have some augmented office hours at various points, probably after the exam. We'll try to get the TAs out to give you guys some help over the last couple days. The only other thing I was going to say about assignment 3. Oh, right. So this week we've moved a couple of office hours around. So please check the calendar before you come in. I think we moved some of Jinghao's from tomorrow to Thursday. So we have Thursday morning office hours, but some of the ones for today and tomorrow that Jinghao would normally do, he won't be doing. In some cases, that'll just mean there are 1 fewer TA there. In other cases, those office hours got moved. So just check the calendar before you come in. All right, any questions about wrapping up the end of the year? Yeah. Good question. I will get on the TAs to sort of get through that, right? And I could start helping too. I'm sure you guys love when I grade your questions. Right? Gives you that like little special feeling. Ooh, Jeff graded this. Oh man, he hated my answer. Yeah, so I'll look into that and we'll help. But the same, there was some kvetching about this after assignment 2. Now clearly the assignment 3 deadline is not moving, right? Period. I'm not joking this time. There's nowhere for it to go, right? I have to turn in grades, I think, by Monday or something. So there's no way that we can move it anymore. Same caveat applies. If you want a chance to revisit your assignment 3 design documents, you need to get them in early enough so that we can look at them. I would probably say, to be safe, if you want a chance to revise code reading and design doc questions, please have them in by a week before, right? So by this Thursday, right? And I will make sure that me and the TAs are keeping up with the grading as much as possible to get through the design documents maybe by early next week, so you guys have a chance to determine it. But if you submit them 2 hours before the deadline, no, you're not going to get a second chance, right? Sorry, that's just that's not cool. All right, so GFS. So again, so let's set some context here, right? There were several decades of work on network file systems, which many of you have probably used without knowing it, right? So Timberlake and a lot of shared login machines in order to provide a consistent file system that you can access from multiple machines will mount what's called a network file system, right? I don't know. I mean, maybe you're like me. It took me a long time to realize the implications of this. I remember thinking, man, there are certain things that run so much faster on my local machine than they do on the shared login machines that I would use at Harvard, right? And that's because my local machine had a real physical disk sitting right there. And the shared login machines, every file operation essentially required communicating with some central server. So NFS, which is probably what a lot of these machines are using, was designed for environments where you have sort of a small number of machines in a fairly controlled environment. Early versions of NFS, there was actually no authentication or no sort of handshaking to determine who clients were. So if you wanted to, on NFS mounts, you could actually change your user ID locally and then inspect somebody else's files on the NSF mount, right? Because NSF had no idea who you were, right? Depending on how it was configured. But that was sort of the design point of NFS, right? And NFS, you can think of NFS as essentially taking the file system interface and implementing that on the client, but all actual chunk operations, anytime something needs to get read or written from disk, that all goes to a server, right? So there are all these requests flying around saying, give me this chunk of this file, right? And that request goes out over the network now. Hopefully it doesn't go very far. The server grabs it and responds with the data, right? And then you can do caching in NFS. But NFS was really never designed for sort of large scale environments where people were accessing the file system from a lot of different places, right? It's most suited to, and this is still where you see it deployed, right? A couple of different machines in a single cluster that all want to share a file system, right? NFS is a good fit for this. So, and then there was also a couple of decades worth of work on more distributed file systems, right? So you can think of NFS as a sort of a locally distributed file system, but again, it's not built for the mode of operation where you're at home and you want to mount a network file system on your local device, right? NFS, the sort of authentication mechanisms that early versions of NFS used weren't really appropriate for that type of operation, and NFS's performance over those links was not very good, because it didn't do a lot of local caching. So there were other projects that looked at building more distributed file systems, right? There were variants of NFS. There were whole new projects that started off trying to build these. And these were, and then you can imagine as you start to have more and more distributed file systems, a couple of things get difficult, right? One is providing performance, right? The other is making certain type of file operations consistent, right? So if you have a lot of people modifying the same files from different places, the network introduces latency, you can have disconnected operation, et cetera, et cetera. So there's all these sort of challenges that are built in here, right? So now we fast forward to 2003, and Google comes along and publishes this paper on the Google file system, right? So where does Google position itself as far as making a contribution in this space? They talk in the introduction about several things about the Google file system that make it interesting, right? Different things that make this a unique sort of research contribution. So what are some of the claims that they make about why they are different from previous attempts to build distributed file systems? Some of them are up on the board, actually, right? But they lay this out very consistently in the introduction, right? So what's different about Google's environment, about its workloads? What have they really done here, right? Is GFS a general purpose file system? I mean, maybe that's a leading question. Yeah.
They say they append most of the times and they never change the already written file.
So what are we getting at here, right? Google has, a lot of file systems. We go back to thinking about when we talked about file systems, right? And performance. What's one way to improve the performance of any file system? If I take a file system that's built as a general purpose file system, and I want to improve its performance, what's a general approach? Yeah.
Tailor it to your workload and your specifications.
Yeah, so there's a couple of things you can do, and they've done a couple of them, right? Number one is I can tailor it very closely to the specifics of my workload, right? So Google's, if you read the paper, there's all these like services lurking in the background, right? They never say what they are, right? They're just like, oh, we're Google. We built this file system for a variety of reasons, right? But you can imagine what they are, right? And we'll talk a little bit as we go through the paper about, how things like search, for example, which is a little part of what Google does, might actually use some of these tools, right? And why maybe they were sort of tailor-made for some of these workloads, right? So the first thing is I can study my workloads and I can optimize my workloads, right? What else can I do? What's another way of improving performance? Yeah, Paul. Yeah, so remember, this is not a publicly available file system. It's not built for general purpose use. They don't have to take some sort of legacy app and have it run on GFS. GFS is built for a specific set of apps that are built to use GFS, right? So I can create coupling now between my application and the underlying file system. Where is this particularly significant? There's a couple of places, right? There's two sort of key aspects of GFS that take advantage of this. What's one of them? Or you can think of them as falling into two different categories. Two places where GFS exploits properties or the ability to interact with the application. Paul, what's one? Yeah, so these relaxed consistency properties, right? Providing, if you want to study this and read a bunch of distributed file systems papers, creating a globally consistent file system under the variety of conditions that distributed file systems are going to experience is extremely difficult, right? And in fact, how many people have ever heard of the CAP theorem before? Nobody's taking Steve's class? Yeah, so the CAP theorem, which is a very famous sort of law in distributed systems building, says that it is impossible to design a system that achieves three properties simultaneously. Those properties being consistency, it always is consistent, showing the same view to all clients. Availability, the entire system is always available. And the third one is resistance to network partitions, right? So if part of my distributed system gets cut off from another part of my distributed system, then I need to sacrifice one of those two. So the idea is you can get any two out of the three. I can make a system that's consistent and available, but does not resistant to network partitions. I can make a system that is resistant to network partitions and available, but not consistent, right? And this is a really elegant result. You can kind of think through in your head probably how different parts of that theorem being violated makes the other parts more difficult, or having one, relaxing one allows you to achieve the others, right? So all these earlier distributed file systems, were, the goal was to provide these sorts of guarantees, right, to work around some of these sorts of failures. And GFS says, you know what? We're just going to make the app deal with some of these consistency problems, right? So one thing was with, think about how you would have to change your app to deal with running on GFS. One is that you would have to handle some of these failures that GFS creates, or the modifications to the file and the way the files are structured that GFS creates to work around some of the problems that GFS deals with. What's the other thing you would have to do? You'd have to modify your app to deal with GFS sort of relaxed consistency model. What else does GFS change about the typical file interface? Yeah. Well, I can do random writes, right? It just says the performance of random writes is going to suck, right? They support the traditional Unix file system interface, although they're not implementing this as a Unix file system, right? This is implemented as a user space daemon that uses the file system locally to store information, right? So that's kind of interesting. But I can still do all the typical operations, although again, they don't make guarantees about some of them because they argue that their workload doesn't need them. But what have they added that traditional file systems don't have? What operation here have they introduced that's a good fit for their workloads, they claim, and is missing from the traditional POSIX file system interface? Let's want to try again? Yeah. Yeah, not replication. I can do that in other file systems. This is something that's visible to the client. Yeah.
Snapshot?
Nope. Other systems can do snapshots. Yeah.
Atomic append.
Yeah, and it's not even atomic append. It's this record append, right? Which we'll talk about in a little bit. So they've introduced a new feature, right? This is something that, and again, if I wrote my files, if I tried to run if I took a traditional app and tried to run it on GFS, as long as I can deal with the consistency differences, it could work fine, but it's not going to take advantage of this feature, right? This new record append, record append. I always say it wrong. Record append that GFS introduces, right? We'll talk about the semantics of that in a little bit. It's kind of interesting. Well, okay, so what's another difference, right? I think we've gotten two out of the four differences from traditional distributed file systems that they identify. There's another one that's related to a characteristic of their workload. It's not quite the same thing. What kind of files is GFS designed to support? Yeah, Matt. Huge files, right? These are big, right? And so why? Why is this, right? They talk a little bit actually about how they've restructured some of their apps, right? To use this, but why do they argue that they only need to support huge files? Not a trick question. Yeah. Because that's what their applications use, right? And that's what's generated by the workloads that they're discussing, right? These workloads that generate massive amounts of information into a single file, right? And then also typically read massive amounts of information from a file sequence, right? And when we get into the specifics, we'll talk a little bit about, you can start to imagine how would the combination of web crawling and web indexing use a system like this, right? Because again, that's what's lurking behind this paper, right? It's this idea that this is a file system built to support search type applications. Primarily, it's used for other things, right? They talk about using it for some other types of purposes, but this is largely what seems to be behind it, right? And there's one more, right? There's one more difference that was related to something we talked about last class, I think, actually. It starts to feel like RAID because why? Distributed file systems achieve scalability. What kind of hardware is Google running on circa 2003? Yeah, Natasha.
Bought off-the-shelf computers so they fail a lot.
Yeah, commodity hardware, right? Commodity hardware with large numbers of failures. So they're trying to build a performant, scalable, reasonably consistent within its requirements file system on top of cheap, crappy disks, basically, right? Cheap, crappy commodity drives. But that's the thing, right? Think about it. If what Google sort of said as a design principle with this paper is, and with the design of their early servers was, you know what? Cheap disks are cheap, right? They're crappy, they break a lot, their performance is okay, but in terms of dollar per byte, they're pretty good, right? And that starts to sound a lot like RAID, right? It's probably not only dollar per byte, it's dollar per transfer byte, right? How fast can I get data on and off these disks? Turns out that that's a good sweet spot if you can build a reliable system on top of it, right? So this is sort of what GFS is, right? So the four things, right? One is it's tailored very much to their workloads. The second is it breaks applications, so they're writing applications on top of it. Third one is built on top of commodity hardware, and the fourth one is really designed to support large files, right? All right, so what are the three parts of GFS? If I look at the parts of the GFS system, I can break down the machines used in it into three categories. There's three types of machines. What's one of them? It's an easy one that should come right off. Yeah. The master, yeah. James is going to bring up the master, right? So I was thinking someone would say a client, because that's clearly what you need, right? So I have a master, right? How many masters are there? One, right? You know, there's only one master. Come on. If you have two masters, then one of them's not really the master. And then I have clients, right? What are clients? Clients use the file system, right? Clients are running applications that do something with the file system. And then what's the third part of the architecture?
Chunk servers.
Yeah, my chunk servers, right? So let me bring up the next part of the paper, right? Whoops. Right, so I've got, actually, look at this, right? So I have my master, I have my client, which is running applications, and then I have any number of chunk servers, okay? What is the, you know, I think you guys have some sense of what the client does, right? Which is it issues requests to open files, to modify files. They have a funny name for modifying files. What do they call it? Who read the paper? What do they call modifying files? Mutations. Yeah, data mutations. Right, it's kind of funny. So this is the general architecture. I have one master, right? What is the master responsible for? Right? The clients are using the file system. We have some idea of what they're doing, right? What is the master in charge of doing? Yeah. Yeah, so the master will do some positioning and replication of chunks within the file system, right? So why would I need to replicate chunks? Yeah. Yeah, remember, cheap crappy disks, right? That fail all the time. So if I don't have something written down in multiple places, I don't have it in a secure, reliable way, right? So one of the things that the master will do, and this is sort of like more of the complex, you know, hairy, cool stuff, is adaptively decide what chunk servers should be storing which chunks, right? So we've talked a little bit about what chunk servers do. Chunk servers clearly store chunks, right? So they store portions of a file on their local file system. What else do they have to do? Yeah. Yeah, so that's where the data is, right? So if the data is going to get to the client, which wants to use it, then the chunk servers have to be involved in transferring and updating chunks, right? What? So, guys, I'm getting this sense. How many people have taken or are taking Steve's distributed systems class? Oh, you guys should be all over this stuff. Come on. All right, I'm going to start picking on that group. What's a potential problem with this architecture, right? Where are a couple? So whenever you're building a distributed system, you worry about bottlenecks, right? I have a bunch of machines, and ideally what I want is load balanced across the machines, right? This is to some degree similar to how we've talked about using other resources on local machines when they're managed by the operating system, right? But this is now over a bunch of machines. If I have one machine that's pegged, you know, its disk is going as fast as it can, and its CPU is completely redlined, and the rest of the machines are not doing anything, I don't have a good distributed system, right? Because there's a bunch of resources out there that are underutilized. So what's a potential source of bottlenecks in a system like this? Yeah. The master, right? What do you guys who are taking distributed systems, what do you guys call this? The single point of failure, right? It's not only a single point of failure, because if the master fails, then there are operations that can't immediately proceed, but it also is a potential bottleneck, right? If the master is overly involved in operations that are being performed within the distributed file system, then it's possible that the master will be very busy, whereas the chunk servers and the clients are idle, right? So it's not what we want. How does GFS mitigate this? So remember, the GFS does some nice things. First of all, the master maintains the authoritative namespace, right? By namespace, we mean, this is similar to a traditional file system, a mapping between a path and essentially the information that's in a traditional inode, right? What chunks, right? I have a bunch of chunks out there stored on some chunk server somewhere, right? What chunks correspond to that file, right? The master maintains this authoritative namespace. So the master is in charge, right? That's why you call it the master. So, if you want to rename a file, if you want to delete a file, the master has to be contacted and informed that this is happening, and it doesn't happen until the master says so, right? However, so this sounds like this is getting bad, right? How do I, now the master is essentially involved in every operation that takes place on the file system. Is this true or false? How do I get the master out of the loop? Yeah.
False, because you can read without consulting the master.
Well, can I read without consulting the master? Yeah.
So the master has to issue a lease so that temporarily the client can just directly access the chunk server, but when it runs out, then it can't.
Well, but let's keep in mind, right? So they talk later in the paper about sort of separating what they call data flow and control flow, right? And if we get time, we'll talk about that a little bit more. But so let's say we'll walk through the process of writing to a file, right? But let's say I want to open a file. What is the process for doing this? I have some path that I want to open, right? Where is the data corresponding to that file? It's on some of these chunk servers, right? Like some of these sort of hundreds of chunk servers have the chunks I want. When I open a file, do I know which ones do?
No.
I have no idea, right? So how do I find out? I ask the master, right? But what does the master tell me? I say to the master, here's a path, right? What is the master going to tell me about that path if I want to read from a file, for example? What's going to be the next step? Yeah, it tells me, hey, here are the chunk servers that have the chunks that you want, right? So the nice thing is, well, there's a little bit, again, so I ask file name, right? And it gives me chunk handle and chunk locations, right? Now, the nice thing, and they've nicely used sort of thick and thin bars, this is a lightweight operation, right? This is only, one network request, and I get a small packet back that tells me everything I need to know. Where does the data come from? From the chunk servers, right? So here's this really fat, data flow diagram. And now the idea is once I know what the chunk handles are, and don't worry about the byte range, who cares, right? I mean, that's just so I can get the parts of the file I want, clearly. But now I can contact the chunk servers, and the chunk servers are actually going to be the ones who are going to be involved with transferring the data to the client, right? So the idea is, if I want to prevent the master from being a bottleneck, I move it off the critical path as much as possible, right? And this is a classic feature of these type of systems. I want as many operations as possible to be able to proceed without contacting the master, right? Any questions about this? This is sort of, if you haven't seen this before, it's very elegant. Once you see it a few times, it becomes kind of still elegant, but normal, yeah.
The master is still a single point of failure, right? I mean,
Right.
if the master fails, then how is it going to get the file?
Right, so how do they deal with master failures, right? Remember, these are all cheap, crappy disks mounted on cheap, crappy machines, right? And the master is run on just the same kind of cheap, crappy machine as what runs the rest of the system. So how do you deal with this? Yeah. Yeah, so the idea is the master state, and this starts to sound, if you guys read this part of the paper where it talked about how the master stores operations that happen to the file system, what did it start to sound a lot like, which you guys have studied already in this class? What's that? In this class, yeah. No, this is not Paxos. Paxos is like 60 times more complicated than this, right? This is simple, right? But what is so the master, this is a problem, right? So the idea is that the master is storing some metadata about the file system, right? If the master fails, what do I want to be able to do? There's two ways that I might need to recover the system. What's one? Right, so when would I need to choose a new master? In what cases, let's say the master fails, right? In what cases would I need to pick a new master? Clearly I need to pick a new master, right? The file system is down until I have a new master, right? Someone's got to be in charge, right? But when do I pick a new client to be the master? How about if the master is in a data center that was just hit by a nuclear weapon, right? That master is not going to come up again, right? And that's a little bit of a dramatic example, right? But maybe the power went out to that rack, right? That master is not coming up again to take over, right? So there's two types of master failure. One is if the master crashes and can be restarted, right? The second is if the master fails and a new master needs to be chosen because the machine died or the power's out or whatever, right? So in both those cases, what do I need? What does the new master need to be able to do in order to come up and restart the system? And this starts to sound very similar to something. Adam.
Up with the previous master left off.
Yeah, I need to be able to bring the Google file system into a consistent state. So where have we seen this problem before, Natasha? Journaling. And that's basically what they do, right? Google basically journals changes to the namespace that are maintained by the master. That journal needs to be replicated somewhere else so that if the master like really dies, like the machine is toast, the disk is gone, I have another copy of it. When I bring up the second master, they have a very similar sort of record and replay process that they use to bring the Google file system back into a consistent state, at which point I can start running the file system again and responding to client requests, right? So they talk, so what's the main thing? So again, master, still single point of failure. What is the main argument that they make about why this isn't a problem? The master will fail, right? But that failure might be okay if what? What starts to determine how much of a problem that failure is? Yeah?
How much the clients can notice.
Well, okay, so what determines how much the clients can notice? What determines how long the file system is going to be down for? Yeah, Doug.
How long it takes to rebuild the namespace?
Well, okay, so that's a part of the general process of what? What's that? No, we don't need to delete our election, right? This is not a peer-to-peer system, right? This is important though. Someone else from outside the system is going to just choose the master, right? They say that explicitly. Some service from outside GFS that we're assuming is going to still be online is going to choose a new master, but then I have to do what? Bring it online, right? But if I can bring that, if I can detect that the master has failed quickly and bring up a new master quickly, then the disruption of the file system is minimal, right? So it doesn't matter. Single point of failure, fine, right? If I can fail over, right, in only a second or a minute, then who cares, right? The overall availability of the system is still going to be quite good, right? So what's something else? It's an interesting question. Does the master in the Google file system, so we said that the master is the authoritative source for namespace operations, right? Anything that changes the namespace, right? Moving a file, creating a file, things like this. What is it not an authoritative source for? What in general does the master not always have a complete view of? Yeah. Well, what about data in particular? Okay, well, yeah, the master doesn't store any file contents, right? But what other piece of metadata about the system does the master not necessarily know? Or is not an authoritative source for? Yes. No. So the master is mapping paths to chunks, right? And chunk locations. What part of that process does it not necessarily always know?
The internal things how much is written and
No, fair enough. It doesn't know anything about data. I'm not talking about that. What about the metadata of the system? Does GFS allow the master to discover? Yeah, Gabriel.
If a chunk is being accessed or not.
So that's true too. It's not, and that one I'm after though. It's a really fundamental part of the system. Paul. Chunk locations, right? Remember, so let's say a chunk server fails, right? Or let's say I rename a chunk server. Or let's say I bring up a new chunk server that has existing chunks on it. What's the first thing that chunk server does? Yeah. Yeah, so that's how the master finds out where chunks are, right? Clients tell it. And they said that they experimented with a version of the system where the master was actually the authoritative source for where chunks were. And this was simpler, right? Because look, who's the authoritative source for which chunks I have on disk if I'm a chunk server? Me, right? The master shouldn't be telling me where things are. It doesn't even know. I failed and I didn't even write those 3 chunks that it thought were there, right? Or again, in another case, I can rename a chunk server, and so the master's like, huh, I told Tom to store those chunks, and Bob came up and told me he had a bunch of those chunks. Yeah, whatever, right? So this is nice. It's a nice feature because to some degree it doesn't need to know this, right? All right, so let's go down and walk through the process of doing a write. Where to go? Okay. Right. So here is a write. We'll go through the process here. Right.
Question.
Yeah.
So as far as locality goes, the masters and the chunk servers can be in completely different locations.
Yeah.
Of the world.
Yeah, but would I do that? Is that really what this is designed for? Not really. I mean, this is designed to build a distributed file system inside a data center, right? So yes, I could technically put things in different places. I don't know how well some of these features would work in that environment, right? It's really built for I've got 100 machines kicking around in my data center, and I want to use them to build some sort of big, fast file system, right? All right, so going sort of slowly, maybe think about sort of what I want to cover. Okay, so let's talk a little bit about this, about the consistency model, but in particular, let's talk about this new operation that they introduced called record append. I don't even know where it is in the paper. So what is record append? So GFS supports traditional append operations. What does GFS consider a traditional append? Let's say I want to append to a file. You guys have done assignment 2 by now, right? What does an append essentially boil down to? Is there a special append system call? No. So what's an append? It's a write to where? The end of the file, right? I find out where the end of the file is, and I write, right? If I open a file with append, all it means is that that's where the initial file pointer is placed, right? At the end of the file. What happens if 2 processes append to the same file at the same time? Well, I mean, let's say in the best case, right? Let's say I can make this consistent. What does it look like to the file system? It looks like 2 writes, right, to the same place. So what should happen? What would be the best thing to happen, right? Yeah. Yeah, somebody wins, right? I don't want like little bits of both writes, right? Like that's bad, right? That's the worst case scenario. There isn't like a golden best case scenario here, because essentially what's happened is that, so the problem here boils down to something interesting, which is that the operating system doesn't really understand what the application is trying to do, right? All it sees is 2 writes to the same part of the file at the same time. Now it's possible that an application is written so that that's okay, right? So the operating system is like, you know what? I don't know what to do with these two requests. I will make sure that one of them wins, right? So what will happen is that somebody will write to the end of the file, and the other person's write will be lost. Now in Google's workload, what do they want to happen? It's an interesting new file system feature, right? What does Google clearly want to happen in this case when I have multiple writers writing to the same file? Or what do they want to create a new way to happen? Yeah. Nope. That's not what I want to do. I want something to happen. That something is what? They want to report it? Nah. Well, again, remember, this is not record append. It's record append, right? That pronunciation change is actually important to understanding what this is doing, right? It's not recording, it's appending a record, right? So what do they want to happen? These 2 simultaneous operations hit the file. What do they want?
Multiple people can append to different parts of the file. So just the append.
going in the right direction. But again, 2 simultaneous appends. The normal behavior is one of them wins, the other one's lost. Google wants what to happen? Yeah, Paul. Okay. I think you're getting in the right direction. They want them both in the file, right? Both of the appends should be able to append to the file, right? What do I not know what's going to happen? The order. Who cares, though, right? They're essentially saying, for some of their workloads, what matters when I have multiple writers writing to the same file is not that one writer wrote to a particular byte region and the second wrote to the other. No, just that all the data is preserved in the file, right? Doesn't matter what the order is, just has to be there. So when I have multiple concurrent record appends, right? Like a record, right? Like an indivisible unit I want in the file. I don't care where it is, I just want it to be there, right? So that's this new feature that they've added to the Google file system. Who can think of a way that this might be used by like a search type operation? I have a big data center that I'm using to build these search results, right? So what might create a little scenario where this happens? Yeah.
Multiple crawlers writing to the, as they discover new sites, they keep adding to a single file.
Yeah. I mean, think about it. Let's say I'm trying to index Britney Spears, right? Clearly, I need multiple crawlers to do this, right? I can't run this on one crawler, right? A crawler would take weeks, right? So I split it up. I run it on 10 crawlers, right? The index file so essentially the output here that I'm going to use to build an index is just a list of all the sites that the crawler found that had Britney Spears, right? And so what's happening is as the crawlers are going along, they're building up a record, right? The record you can think of as a list of every site that has this term. And what they're going to do periodically is they're going to push that record to the end of some log, right? And that log of all the sites that match the term, I have no idea if this is how this works. By the way, I don't work at Google, right? It's just a hypothetical, scenario. But that log is going to be processed later, and the ordering within the log doesn't matter, right? All that matters is that everything that the crawlers found ends up in the log, right? So GFS added support for this feature specifically so that they could support these types of operations, right? All right. Oh man, I wish we could get into some of the cool stuff here about the ordering of writes, but I think we're going to skip over that in the interest of time. Let's just look at. So you guys can look through all this beautiful stuff later. It's very cool. Master replication, yada yada yada, data integrity. All right. So let's just look at the measurements that they did, right? And here, what they're trying to, and actually let's look at these two. So one of the things they do is they compare two different, remember, they're running a bunch of different things on GFS, right? Some of the things they're running are production workloads that are doing useful stuff. Other things they're running are sort of research and experimentation and development-oriented workloads where it's people, right, who are firing off big jobs to do various types of data processing, right? So they compare two clusters, right? Cluster A is their sort of R&D cluster, and cluster B is a production GFS cluster that's running production data processing, right? So this is cool, right? I mean, these clusters are providing 180 terabytes of disk space. It's pretty awesome. How many people have a terabyte of disk space? How many people have 180 terabytes of disk space? Yeah. The number of files is pretty similar. The number of dead files is quite a bit higher here in their production environment. Why would that be? So dead files, remember, are files that the system has created new versions of, and it hasn't deleted the old versions because it doesn't do that immediately. It only does it at times when it needs space. So why would the production environment be generating so many dead files? Yeah. Not necessarily. What do these systems do? Yeah. Well, but there's a lot more dead files even proportional to the space, right? So I mean, there's 5 times more dead files, even given that the file system is only about twice as large. Yeah. multiple copies of certain files. We're getting warmer, right? Remember, old dead files are old versions of files that aren't up to date anymore, right? What is a production workload? What might a production workload be doing? Yeah, it's updating stuff, right? Hey, it's a new day. I got to rebuild my index for Britney Spears, right? It's changed since yesterday, right? I've got to rebuild it. So every time I rebuild it, there's a bunch of files that are essentially no longer valid, right? They're reversioned, they're recreated based on my new crawling results, right? So to some degree, it makes sense that the production system is generating a lot more dead files because it's just keeping things up to date, right? So when they start to look at performance, they're actually looking at what's the ultimate bottleneck here? That's a good question. What's the ultimate bottleneck for a distributed file system like this? What's the thing that I'm going to saturate at some point, and then there's no going back, right? What do you think is the weakest link in a file system in a data center like this? Yeah, Adam. What's that? Yeah, the network, right? This is a network-oriented file system, and they already admit early in the paper that they don't do a lot of caching on clients because they assume they don't need to. So network bandwidth is what's going to be the bottleneck here. Now, how do I tell if a system like this is achieving full performance then? What would I like to see? Yeah, but what should the bandwidth utilization be? Yeah, I want 100%, right? If I've got a gigabit Ethernet link, that thing better be pushing a gigabit, right? If it's not, then there's something else in the system that's slowing things down, right? And what they say is that, we're doing pretty well, right? So a gigabit is 125 byte per second link, right? And their read workload is getting about 80% of the per client bandwidth limit. That's reasonable, right? The write workload is a little bit slower, right? So here's a question. They say that as the number of readers increases, well, this is just right on there, so I'm not going to ask that question. Can you guys read this from the back? Maybe that's why no one is answering. I should blow it up, right? I'm talking about a paper that no one can actually see, right? Like something very like performance art, you know? Like check out that paragraph. It's pretty awesome. All right, so I think this is enough about GFS. There was a lot we didn't get a chance to cover, but I think, given your background distributed file systems, this is pretty reasonable. Any other questions? Any questions about GFS that I can? Yeah. What's that? The order of the writes matters. I think. Sure. Right? I mean, any traditional file system operation, so they have a description earlier in the paper that I had to read about 3 or 4 times before I even sort of understood it. They talk about their consistency guarantees with respect to different types of file operations, right? But because a lot of, so essentially what they've gotten around this with, right, is this record append primitive, right? There, the order of the writes doesn't matter, right? So if I can move a lot of my workloads to using this as a primitive, then I can improve things. If I have multiple concurrent actual writes to the same chunk of the file, I have the same sort of consistency problems that I would even on a local file system, right? They don't try to make any guarantees about this, right? Yeah.
Is GFS and fair game for the time?
Sure. Design, well, I mean, I'm not going to, let's put it this way. What we talked about in class about these systems is fair game, right? I'm not going to quiz you on, who chooses the modification order in GFS when there are between the primary chunk server and the backup chunk servers, right? Which is cool, but not going to be on the file, right? But if we talked about it in class, then it might be, right? Really, what these couple of papers are giving you guys a chance to get used to is looking at new systems, right? And trying to understand something about them and trying to use some of the design principles that we've talked about in class to solve problems or think, deductively about how they work, right? That will be on the final, right? And if you look at the last couple of years' exams, I enjoy finding research, sort of picking up good exam questions from recent research operating systems, right? And they'll be, I'm not going to like put a paper. Actually, that would be fun. I know I did that one. Just append 3 research papers to the exam and have questions about them. No, that would be unfair. Right? So there'll be a sort of simplified and high-level overview of the system, and then you'll be asked some questions about it. Any other questions? Good questions. All right, we'll see you on Wednesday when we'll talk about Linux scalability.